let's move on into our next speaker in the session. I've known Mike Liehr since AIM was just an inkling in his eye. So imagine for the rest of the audience that you were given hundreds of millions of dollars, like you hit the lottery. But instead of like hanging out on a beach drinking endless drinks with umbrellas in them, you're asked to create a startup in 5 years and be fully functional and self-sustaining and all that. And you have a little bit of idea what the challenge is that Michael has in front of him. Let me give you a little, but he's certainly up to the task. And I'll give a quick introduction here. He's the CEO of AIM Photonics. He focuses on the creation of the new business opportunities for AIM and is responsible for the effective and efficient operation of AIM's programs, including SUNY Poly's strategic 300mm integrated photonics, semiconductor, and 3D packaging. He's also the Vice President of SUNY Polytechnic's Institute for Research and the Executive President for Technology and Innovation. Prior to this recent assignment, he led the global 450mm consortium through the startup phase as the general manager and was an IBM distinguished engineer. Thanks a lot.
Thank you. So I need to start this out with a small correction of what Kim said earlier. He said, we are a startup that's 2.5 years old. We're really, in my book, only 2 years old. I spent the first 6 months of this institute talking to lawyers. I'm really only 25 years old. See what that 6 months did to me. Again, that was really to establish the membership agreement. And at the end, about January or so of 2016 is when we started to put in place what you're going to see here. Just like my predecessor here, I have a whole bunch of charts. I'm going to take you through them fairly quickly, not going into many of the words that are on these charts. I would like to give you an update on where we are and what we have accomplished. But then secondly, after that, I would like to take you into a transition that we're going through at AIM, which has a lot to do with the statement that Alan just made. The federal funding that we have received is only good for 5 years. So we have a little less than 3 years left, and that means we really have to seriously talk about what AIM will do and how it'll look in 3 years from now. So 2 portions of what I'm going to say. All right, you all know this, but again, compared to my predecessor here, I'm not going into the system level aspects at all. I'll sort of remain in the bowels of the steamship where folks are shoveling the coal, basically establishing the infrastructure that is required to build the kind of chips that you might want to use for any applications. In our book, we're looking at these 4 elements as being part of our ecosystem. It certainly starts with electronic photonic design, go into both indium phosphide and silicon foundry services. And I will speak very little about the indium phosphide portion of it because you have Gloria here who will speak a little later about what Infinera does. So I'll just mention that in passing, and I'm focusing on the silicon component. There's clearly packaging and test. This is the most expensive part of any photonic assembly. So from a cost reduction perspective, we pay a lot of attention to it. And then last but not least, where needed, you have an optical connector. So here I'm now focusing a little bit on SUNY Poly. Think of SUNY Poly as a member of AIM, but also as the underlying foundry behind AIM. AIM is a consortium that has the customer interface and makes the decisions on where we want to invest our resources. And as a foundry, SUNY Poly would be the one both from a wafer fab, but also from a packaging assembly and test perspective. And I'll take you through these things. You see these 4 boxes here. Those are the areas that I'll focus on during this presentation here. And at the bottom, you see the host of folks that we're working with, both from a design methodology perspective, from a enabling perspective as far as masks and assembly of a reticle is concerned, and then some of our technology providers and key customers that we're working with internally. I'm occasionally flashing pictures of the folks, that some of which are here that you should be able to talk to as you're going through the next 2 days. So you see in the top right Rich Bush, who is basically our director for enablement in AIM. And the point of this chart here is really to make 2 points. First of all, we really believe in hierarchical designs, and this has a lot to do with time to market. If you're starting at Maxwell's equation to design your chip, you are bound to take a long time. We really like to advocate a system where, just like in the semiconductor industry, you gain productivity by having preconceived library elements, a PDK, and you're using these things in order, again, to gain time to market. So we're putting these elements in place. Obviously, we're looking for customers, companies to come to us to help define what those elements should be, but I'll give you at least one example of what we mean by that. And then secondly, system-level co-design, and that should include packaging, but you do need to be able to co-design the control ASIC that your switch, for example, would have, as well as the optical fabric that you have in a switch, for example. Oh, and I did forget to mention at the bottom of this, we do support small and medium-sized companies, a lot of which do not have the design resources to actually do this. So while we're not supporting at the moment, there's a lot of discussions about, can we support design services? This is apparently not at this point very frequently available. There are two entities that I'm aware of. They're both European. So certainly within the US, it doesn't seem to be available. So we're talking about making that available. And you can certainly talk to either Kim or myself about what we're thinking about in that space. We are offering a PDK. I use the word PDK here in a sense to describe both the basic elements of the PDK that support the design methodologies, but also a component library. And you see at the bottom here a list of those components. As you can see from the picture, we have really focused on transceivers. So this is one area where we have built a complete set of IP blocks that it would take to build one of those. And you see this is a presentation, or from a presentation that was just given a couple of weeks ago at OFC by Armin. I'm not sure Armin is here, but he is in the area, so feel free to talk to him or to Mike Watts from Analog Photonics. Analog Photonics and us form sort of a part of an ecosystem where these elements are provided by Analog Photonics. We are the foundry. He is sort of the IP provider. This is, again, an example, same example that I just talked about, where what you really want to do is look at the various components, how they perform, and what kind of product you can build with this. We are not at this stage yet where we've demonstrated this all being put together and then building one of these. This is something that we're actively discussing, but we have, as I said, put together this library in order to at least showcase what the capability of the underlying technology is. As I mentioned just a minute ago, we are open to discussions with customers in different application segments. We obviously need to pick segments where there's a likelihood of significant volumes that allow us, all of us, to raise everybody's boats here. Okay, so now I'm getting a little more to the heart of this whole discussion. So these are the manufacturing centers of excellence, and you can see what we mean by that, at least on the silicon side. I have shown the logo of Infinero. There is a similar offering on the indium phosphide side that is provided by Infinero. On the silicon side, we have a full-blown 300 millimeter facility. We can literally build a chip from A through Z, about 200 or so 300 millimeter pieces of equipment. We are working on 3.5 laser integration. We do have an active 2.5D and 3D interposer process that we're exercising, one specifically for a customer, the other one more for the MPW program that we're offering. We're in the process of putting integrated inline and optical test in place, and I'll show you in a second what that means. And then we're putting together also an in-house packaging and assembly facility. I'll give you an update on that as well. We do offer currently passive interposer technology, and we are working on to make available early next year active interposer technology. Some of these things you can either talk to us afterwards. Again, I'm not going to go into the details of these integration schemes, but obviously the active interposer would use the PIC as the interposer itself. From a MPW offering, this is what we're currently working on. So we have, as you can see up there, passive photonic waveguide. These are fairly good losses. We're working on improving these more. The passive interposer, again, has TSVs, and we are working at this point on attaching lasers or putting a laser attach process in place, with it being hopefully routinely available towards the end of this year. And the active interposer is also currently being worked on with a goal of it being available in 2019. And up there you see the folks that you would be contacting if you were interested in this program, both from an MPW perspective but also from a process perspective. And these folks were present at OFC. Here's an overview of the MPW program itself. We are starting 4 runs a year at the moment, where the full runs basically serve 2 purposes. A shorter route is just the passive, full route is the active. We offer 2 different chip sizes, and you can see the layout of the reticle there. Most of the tiles are 51 square millimeter, and then one of the tiles is subdivided into 7.5 square millimeter roughly. The idea there is that a lot of the smaller companies as well as universities can't afford a full tile. Therefore, we've carved out that separate offering to lower the price point. As you can see there, from a fab time perspective, it does make quite a bit of difference which one you pick. The numbers that I've started referring to from now on is for the full, which we are trying to get through the fab in 90 days. And then at the bottom, you see by now is slightly dated. I didn't get an update to it. Occupancy levels, so I'm glad to say that these things tend to be fully subscribed. And therefore, I think we have successfully launched this program. Last year was the first time we offered it, so this year is our 2nd year, and you'll see a bit about what we've done in terms of performance enhancement to it. If I can click, there you go. So we're trying to execute this like a real foundry would, again, even though we're more of an R&D foundry in that concept. And you can see our improvement plan for the total processing time. It's been quite a learning experience in 2017, I have to admit. So you can see that initially the first 16 runs were internal to AIM. 2017 were external ones, and then 2018 is all the external. And you can see that both the fab time as well as the time to assemble the tiles, we've made quite a bit of progress there. We realize that there's a lot of education needed in order for folks to really submit something that is reasonably clean from a design perspective. And that's one of the areas where Kim's Educational Workforce Development Program really, really is helpful. I mean, to get this from 75 to 30 days or so, that's what it takes. I mean, tell people more about what we're doing. Internal to SUNY Poly in this case, you can see that we're trying to push down the number of days that it takes in the fab. So you see the DPML, the days per mask level numbers on this plot. Our goal is to get it well below 3. In order to do that, we need additional equipment. That equipment is at this moment being installed, so these are bottleneck tools that we are bringing in both to enhance stability, but certainly also to reduce the cycle time. And Jeff Wetzel at the bottom left is the person who is in charge of making all this happen within our development organization. Again, I'm not going to talk about all the words on this chart. What you see here is, first of all, we have achieved ISO certification. I think that's just one of those things that you need to do if you want to provide a quality offering. We do have regular fab controls, inline electrical testing. Our wafers should come with a report on what the electrical test results were. These are standard foundry characteristics and parameters that we're measuring. We're just now introducing for the first one this year full defect inspection of all the die that are being shipped. And last not least, our optical test, which comes in a second, is being brought up with it being available a little later this year. So we have a inline optical tester from Tokyo Electron here. It's been released for development, and by about the summer or so timeframe, it should be ready to routinely be deployed in measuring the optical characteristics in the scribe line that allow us to control those things as well. And you see examples of what we're going to look at there at the bottom of the chart. So here's how we like to run these MPW ones. The concept here is more that if you're riding on one of these, you get this eventually back to you in the form of die. You measure it, and if you find something wrong in your design, you may have to redo design. So we're allowing some period of time here for you to then catch the next after that. So the MPW1, so as basically riding this wave of of improving your design. This is all assuming that we're not really at the point where first time right, like in ASICs on the electronics side, a lot of designs tend to be first time right. That's not our experience here on the photonics side. Hopefully we get there at some point, but short of that, this is what we're looking at. And you can see that these two ways allow you to do this, again, if you're quick enough in testing and redesigning your design. Otherwise, you may have to skip to the next one over. Okay, how to engage us? I think these charts will be available. But the simple message here is there are two places to go to. I mean, you go to the Moses website. We're using Moses as our aggregator. Download the PDK. Or you come to our own website, aimphotonics.com, and you look at signing up for an MPW1. Our experience is that we would like people to put some money down so we know they're serious. Otherwise, we can't have sufficient number of riders on these MPWs to make them economically viable. But those are the only real concern. There's a bunch of forms that you need to sign, as you can imagine. This gets me now to the test and assembly piece. I mentioned earlier that this is the more expensive part of the whole thing. So we're putting a lot of emphasis on those steps there that you see at the top, the laser attached, the fiber attached, and the connections between the die. A lot of our research projects that we are working collaboratively with Arizona or UCSB, as you can see on that logo there, in order to come up with somewhat revolutionary concepts of how to do this differently. The main problem in all of these on the top is that you have an active optical alignment step involved. That's expensive, it's slow. So what can we come up with that would really shorten the time or avoid the active optical alignment? To support all this, we're building currently a facility in Rochester, and I'll show you in a second where we are with this. This is the status of the TAP facility, and if you just focus on the bottom, so we are towards the end of the first quarter 19. So we're expecting that the facility, the clean room facility, will be ready to accept tools on April 2nd. We try to avoid the April 1st thing, and then move the tools in second quarter. We expect that some customers will come to us and say, look, you bought a wonderful tool set, but that one tool you missed, right? So we have the ability to still buy some of those for the right kind of engagement, as you can imagine. So that's why it says they're as needed. Anything we do from now on obviously will not happen in the second or third quarter. And from a tool qualification perspective, we have a number of customers that are interested in operating in this facility in a variety of engagement modes. One that wants to use it in the second quarter, so we're really looking to see that we have that tool. It's a one particular tool, that tool up and running in the second quarter, so it'll be our first priority. As you can tell, it is really primarily customer-oriented, what we're doing. The customers come to us and we'll bend over backwards to see what we can do to this. Ed White, the picture in the insert, is the person that's in charge of the TAP facility. I would be delinquent to not mention this. There's a program in New York that is very similar to what you have here in Massachusetts. We're encouraging companies to locate. We call this the I90 Corridor, going from Boston all the way to Rochester. There's money available. Obviously, there's fine print that comes with the money. But you should be aware that again, we're looking to settle companies into this area to take advantage of the capabilities that we're putting in place. And there's good coordination between what Massachusetts and New York does in these cases. If you look at the conditions, they're basically carbon copies of each other. So very, very good coordination in this case. So I want to summarize quickly what we have done. We've defined access ramps. This was the 6 months initial process, as well as ways for folks to become members. The roadmap is now really aligned with what we believe the market does. So this is something we did very early on. I think we have a competitive PDK and library, a competitive MPW offering. We continue to refine them. By the third quarter, you'll have the TAP facility up and running. That's what I mean by the full processing capability. And then we do have first commercial engagements. As you might find not surprising, I can't talk about the names of the companies. They don't like their product to be pre-announced. But we have commercial engagements with the goal of producing parts, and we're transferring to volume production to a friendly neighborhood foundry that I can't mention either, because as a foundry organization, we only have so much capacity, so this is a critical step for larger customers. And we also have a number of government-initiated programs that we're in the process of starting up. So that gets me a bit to the last point I wanted to make, since I mentioned that we're going through a transition here. So this is sort of the structure that we pictured originally, how AIM should work, just like a company, a matrix organization with 4 product segments and 4 supporting technology segments. So what we have seen now, especially as we go into sort of the last year, so 2017 primarily, with the color coding of these arrows, the green ones are active programs that are going on as we speak. The yellow ones are the ones I expect to be active as we go through 2018. So we see that there are companies that are coming to us that want to build parts for their own particular product portfolio. And we are encouraging this sort of thing. I mean, we should not be in this section where we develop products. That's not what I want to do. I would like to be the foundry where you do this. Right? So what you see is us migrating to is that our core offering in AIM will be what this red box here delineates. It has the 4 core areas in it, and of course it has AIM Academy with its portfolio, both of road mapping, but also of education and workforce development activities. So this gets me to what probably is the key chart here in this whole presentation. When we were created, the federal government gave us 2 missions. And, one has a few sub-bullets, but bear with me for a second. The first one really is the consortium mission. Right? So as a consortium, we should be coordinating industry needs. This is part of that. We should be building, inventing, and putting into use, enabling manufacturing technologies. You saw some of the researchy things we do that are really aimed at that. And last but not least, we should provide an on-ramp for smaller companies to, basically encourage that creativity that you find in the SMEs. That's what the MPW and the PDK program are primarily about. So you see the bullets underneath there. The consortium projects, we call those Class A in our membership agreement. This means the information that comes out of it is shared among those who are participating in this. And that's potentially a problem for industrial members who don't like their IP to be shared. So we need to offer both. And of course, it focuses on design enablement and MPWA. The second mission is in year 6, this is the US, right? It's not Europe. We are on our own. At least that's what's being said. That means that in year 6, funding dries up. And interestingly enough, I have both state as well as federal funding. So the dry up is fairly substantial, as you can imagine. So this is, the euphemism says, be sustainable in 2021. What we need to do in order to make that happen is we basically have to get to a point where, from an operations perspective, we're profitable, meaning we throw off a small investment capability called profit that we can reinvest in, basically keeping our technology up to date. It needs to be industry product driven, and obviously that allows the government as well. So the government as well as industry are being asked to help us with this. We do need to have sustainable technology advantages. As a member, this is something we spend a lot of time talking about. And then, of course, as I indicated there, we need to provide a path for larger companies to go to a real foundry. You can build early user hardware with us, but not high volumes. I mean, that's not what we're there for. And we need to be able to maintain all the university partnerships, MIT, UCSB, Columbia, and so on, that we have built up in the past 2 or 2.5 years. And if you look at that section, it is really just like the Fraunhofer model. And there's Fraunhofers that have been around for 90 years, so I know this model works if you execute it properly. So we're looking at this and trying to emulate these features that model has. So what are we going to do very specifically now? For 2019, we will change our call for proposal. We really ask that industry or government step up and provide the input that we need into what we call the KTMAs, so the product-driven applications. What we are doing to support this is that we are making the investments in the manufacturing technologies that enable these, should we not be able to do it yet. And the whole idea would be that ideally you come to us with something that we aren't quite capable of doing yet, but that is within reasonable reach, so it's not like way out there. And that basically is a concept that's in the semiconductor industry very pervasive, where you do early access as well as co-development, because systems and technology oftentimes depend enough on each other that you need to co-develop both of them to have a successful program. And the second thing we're trying, and this is something Kim will discuss, it's called application interest group. There's activities within the broader community where industry comes together on their own without being funded by AIM and decides that let's try putting a bunch of pieces together under the AIM Academy umbrella and see what that does. Can we build something? Can we set standards and so on? So we would like to view this as input into our strategy that we use then for our members. And should there be a desire to use our MPW system, by all means, but it needs to be paid because these are non-members that we're talking about. We would like to enable this capability for folks to join, should they so want to. With a membership, then you up in the top bracket again. So these are two approaches, different for different audiences that we really, really like to encourage, again, in the self-interest of being there 3 or 4 years from now. Okay, so and with that, I'm almost at the end. It is very clear that the success of something like AIM depends a lot on the people that we have, and we just give you a compilation here of the folks that we're relying heavily on to make this whole thing work. And with that, I hopefully haven't exceeded my time too much. There you go.
Thank you. Yeah, actually, we do have time for a question or two, if anyone has one. So they're open for business, and
We're a shy crowd.
Kim, you? Yeah.
It's like we don't talk enough already, right? But I think I would like to point out what you said and what we heard in the first talk from Shu. There's a super fab that has been created in Scuba, which is monitoring the same kind of capabilities you have, which points out that 300 millimeter advanced technology node processing is becoming more and more important in silicon photonics, whereas before we thought we could do it with a MEMS fab, right? So what stands between now and the decision to either sacrifice development toward better and better nodes for the long term versus going for more mature technologies in the short term?
I think you'll find that from a technology perspective, and Shu mentioned that as well, 193 immersion lithography is really key. Now these things are becoming available at the 200 millimeter level as well, but it's more than just litho. You have some of the etch processes, CMP. All these things are helping you to minimize roughness. This is something that obviously matters for waveguide and waveguide losses. There are other things that in a advanced technology are possible. We've had the pleasure to work on high mobility channel materials for advanced CMOS. I think the industry has sort of given up on that at the moment, but it came with the ability to bring that kind of materials into our line. As you might imagine, actually indium is a substantial health hazard. I didn't realize that until somebody told me that the threshold for breathable indium was lowered by like 5 orders of magnitude. Same with arsine, is really not very good for you. So there's things that you need to do to a fab, a primarily silicon fab that is, in order to accommodate materials like that. So we've had the pleasure of putting that in. Clearly what we want to do is process these materials in our line. That's the sort of thing that our line is really particularly good at, bringing new stuff in there and then maturing them to a certain point. So 300 millimeter tools bring with them capabilities that just because you had to build a 5 nanometer line, that means that you had to work on sidewall roughness, CMP, technologies that come almost for free because you had to do this for advanced CMOS. We're bringing that to bear for photonics. It's not exactly the same things that matter, but a lot of them are synergistic, so we're just reaping the benefit of that. And you don't get that in an older fab, at least not as easily. You really have to buy all these tools. There's one additional thing that matters quite a bit, and folks may not know that, but the industry went from 200 to 300 millimeter wafers. They introduced FOUPs. FOUPs are basically boxes that the wafers sit in, and the wafer never sees the environment in the clean room. And that's important because no matter how clean you make the clean room, the wafers really don't like it when there's a single dust particle on the window. When you do a 3D full wafer bonding, trust me, it's not pretty. So there's things that the FOUP introduction in 300 millimeter also really helped from a stability perspective as well as from a defect count perspective, not available in 200.
Yeah, very good. I think that summarizes why SUNY Poly is really the expert at this. And if you ever get a chance, you can see how that wafer transfer system up there is very impressive.